So good afternoon, ladies and gentlemen. My name is Frank Mortensen. I'm the publisher of PowerTransformerNews.com. We are a news website providing the people and the companies in the power transformer business with related current information and news. And by the way, we are also providing video live streaming of all the sessions which take place here in the theater. I recently saw a presentation from Ehmcke Wilson. Ehmcke Wilson is the CEO of Wilson Transformers based in the UK. And by the way, also one of the few women in leading positions within our industry. And she figured out that the energy losses of transformers in Europe equal the consumption of entire Denmark. So I think transformer efficiency is a topic of interest. And it's not only about economics and ecology. It is also about standards, efficiency standards, and rules. So today we've got an expert in this field. It's Ben Ehmcke. He is not only a well-known consultant within our industry, but also the publisher of the Impact paper. So I would like to hand over to Ben. We plan to have a short questions and answers session after the presentation, so please, you are invited to think about possible questions also to Ben. So please, Ben.
Okay. Good afternoon. A lot of what I'll be showing, I have to preface that this is from a U.S. market point of view. Now, it also concerns part of the world, but it's from a U.S. market point of view. We say, taking out the next 3%, how efficient are transformers today? Distribution transformers right now are running slightly better than 99% efficient. Some of the standards I'll talk about how that has to change. Power and distribution transformers, very mature product. You talk to the engineers, they haven't changed since Tesla. Basically, no new innovations in several decades. Change is driven by cost and new efficiency standards. What's going on with efficiency standards? We had a new standard in the United States in 2010 that forced distribution transformers to that 99% level. It added 20% more grain-oriented material to a typical transformer. It also added about 20% more copper and aluminum conductor to it. And 30-40% price increase. In the United States, these transformers are considered a commodity. They're not an engineered product, they're a commodity. So all of a sudden we hit the utilities because of a standard with 30% more price. They didn't accept it very well. Right now we have another standard that will take place January 1st, 2016. All distribution transformers, both liquid immersed and dry type. The 2010 standard didn't touch dry type. That standard boosts efficiency by about another 8% for liquid immersed and up to 28% for dry type transformers. Additional materials, additional cost. That's the United States. You just have announced and published the 2020 standard for Europe. All transformers, distribution power, 99.5% efficient. What are the electrical steels that are going to handle that? So we have a large increase in material usage, a magnitude increase in cost, and the IEC, I'm a member of the IEEE Transformer Committee, which is the American version of the IEC. They come to our meetings every quarter, and they say, IEEE, convince the U.S. government to accept the 2020 standard. We haven't. The IEEE does not recommend that at this time. We're worried about materials. But you might as well figure in the United States, once the 2016 standard goes into place, then the next thing we're going to hear is Europe's doing the 2020, we should do the 2020. Well, it's going to come to the U.S. There was also a new standard in Japan this year, which increased the efficiency, moved a lot of Japan over to amorphous, more than there was before. Hitachi's very happy. Again, they're expecting everything to be 99.5% or above. They're doing a lot with specialized metals. The amorphous transformer, the Japanese mills are now making an MOH 070. They also are looking at some things with conductor. I had a conference call last week about them looking at some new exotic alloys of copper that may have slightly higher conductivity. So the Japanese are looking at that also. Asia, most of Asia is copying either the EU or the Japanese standard, including India, the Malaysias. I know that Africa, right now, if they're buying transformers for the United States, they want the transformers from the United States made to the 2016 standard, even if they're going into areas that have never had electricity before. So the standards from the developing countries are now affecting everyone. All the current standards can be met with mid-range electrical steel that's produced today. But for a pole-mounted transformer, you'll never get it on a pole. It'll be way too heavy for any pole to take. The sizes are going to be huge, and the cost is going to be very excessive because of the amount of the materials you have to put into these transformers. So particularly distribution, pole mount and pad mount transformers, they can be met by the current materials. But it will be costly, and it will be at a sacrifice of weight and size. So what are our options? Well, with transformers, there's basically three areas you can look at. It's either material, it's design, or it's innovation. And I said in a previous slide, there hasn't been any real innovation in a long time. So it's about time for something to happen there. Materials, the electrical steels. Better grades are available in some markets. Amorphous metal is limited in availability today. Conductor, the electrical steel will determine the conductor. If you can get the 085s, the 080s, the 075s, then you can continue to use in your low voltage windings aluminum. If you can't get those materials, then you're going back to copper, low and high voltage windings. So we're seeing the move away from aluminum back to copper, which many of the wire companies are thankful for, because the same equipment draws both, but 1 pound of copper draws a certain amount, 1 pound of aluminum draws 3 times the amount. So you tie up the equipment 3 times as long. You're going to see the use of more copper and aluminum strip in distribution transformers. And the tank size will probably increase by 1 tank size in order to accommodate the larger core coils. Design. Latest innovation that I've seen is the 3D core coil. And that's being made right now in China with using both regular GOES and amorphous material. Three cores in a triangular shape with the coils wound at the corners. It's touted that this can make an efficient transformer using less material. That's what they claim. Use a shaped conductor instead of round wire to increase the conductor in the coil. You put round wire into the coil of a transformer, you have air gaps. You want to maximize the efficiency of the transformer while maintaining size, use shaped conductor where you're able to put much more material into the coil while keeping the coil the same size. Look at different coatings on GOES to increase stacking factor. In the U.S. for a long time, we've used what was called light mill glass, a very, very thin coating. We get stacking factors up to 98%. Most of the mills in the world produce what's called a C5 coating, 2 layers of coating. Reduces the stacking factor. If we're trying to squeeze 3% more efficiency out of a transformer, that stacking factor can become part of the equation. And maybe there ought to be a look toward thinner coatings on the electrical steel to help increase that stacking factor. And then design for amorphous cores. That is the last option we want to see in the United States. Well, with the new standards, they will probably, after 2016, take up about 10% of the U.S. market. Innovation. I don't know. There isn't anything really being published on transformers that talks about innovation. A lot of people in this room can add to what we're going to see in the future on transformers. I can tell you, electrical steel, here's where it's made. And there's some new ones on here. And one I don't have Ashler Middle Czech Republic is not on there. I don't have the joint venture that's being developed in India on here. That's where it's made. Right now there's a glut of material in the world of certain grades. If you take a look at those mills that can make material better, M3 or better, cuts down the list. In the United States, laser scribing does us no good. We use a wound core that's annealed, and when you anneal laser scribing, it loses its benefit. Now, all these are based off of the mill's catalogs as of last fall. Amorphous. Met Glass in the U.S., which is part of Hitachi. The 2 mills in Japan of Hitachi. China has subsidized 7 startup amorphous plants. Only 4 are doing production to any degree at the moment. But there are 3 others that are still in startup phase. And there's 1 in Russia. It's only producing about 10 to 15,000 ton a year. It happens to be underwritten by the Russian mills. So this is where your materials are going to come from. People talk about, with these standards, we have to go over to amorphous. These 2, and the one I know of that is running any volume in China, that total output is just about 200,000 ton. Compared to a world demand of electrical steel, what, 2.7 million ton? Or a little better? And we're in a down market still globally on electrical steel, on demand for it. So that 2.7 million ton is probably low to what it can be. So this is a great idea. Will it be ready by 2020? Don't know. Will it be ready for the U.S. market? These can handle what is happening in Asia and the U.S. market 2016. Beyond that, don't know. And that was what I had. I hope that gives you a little overview of what's happening. Everything is dependent. The standard is driving what materials we're going to have and how we use them. And the end result is utilities are going to pay the cost.
Okay. Ben, thank you very much.
Thank you
for this presentation. One question I have from my side. I think one could get the impression from the outside that the improvements in efficiency in the transformer area are more driven by the new standards, the new industry standards, than by decisions made by the owners, made by the utilities. Do you think this is true, and could you explain what could be the reasons?
It's changed over time. Prior to the 1990s, it was driven by the utilities and what they needed to meet their cost ranges for their customers. So the basic standards were built around what the utilities were selling at that time. The environmental groups got into it in the 90s. That's what caused our 2010 standard in the United States. The environmental groups went to the federal government. The federal government said, we're going to establish a new standard. They went to the IEEE and to the manufacturers and to some of the utilities, said, here's what we're proposing for a standard. What's your objections to it? Or do you think we need to go farther? A lot of objections around cost and material. Our government went back and said, okay, we hear you, but here's your new standard. And so IEEE had to write to what the government proposed as a standard. That standard went into effect in 2010. In 2011, the environmental groups went to our Supreme Court and said it didn't go far enough. The Supreme Court said we agreed and went to the Department of Energy and said new standard has to be strict, more strict. That's the 2016 standard. Was the materials really looked at and what impact on materials and cost? No, we just need a stricter standard. That will also be the thing that will probably drive the United States to the 2020 standard. Now, that's all couched in the realm of we get another 3% efficiency out. That's that many fewer power plants we have to build, which is true to a degree. But in the United States, we produce about 600,000 distribution transformers in a year. There are 19.8 million in service, none of which will meet these standards. So how long will it take for all this to flush through? Distribution transformer in the United States, typically 30-year life. So it's not going to have the impact on power plants anytime soon. Now, in Europe, I'm not sure what all the drivers were for the 2020 standard. A lot I've seen are based around the same thing, trying to say the input of new generation capacity. Again, I would think that your distribution base on transformers is not too different from the U.S., other than you make a slightly different design. But I think they're probably in the field just as long. So right now, we're having a lot of outside forces who know nothing about the energy industry that are helping to drive the standards.
Okay, thank you, Ben. What do you guess, to which extent will the production prices of transformers rise in average once they fulfill the new standards?
And I'm not even going to get into what's happening with electrical steel in the United States. That's a much different conversation than what we need here. With the materials that are available, the 2016 standard will increase the cost of a transformer probably another 15%. And for other than dry type, will be another 8 to 10% increase in electrical steel and in conductor. And the conductor part will be even more critical because it will be a move away from lower cost aluminum back to higher cost copper. All that will get passed through to the utility. So, and even if amorphous came on, amorphous could help that, but in the U.S. market, 2016, probably 10% of the U.S. market would be amorphous.
Okay, so thank you. I would like to ask you, the audience, for further questions, please. Everything is clear? All problems are solved for the future? All right. That's very good to know. So, Ben, have you finished? Then? So, thank you for attending our session today, and we wish you a good evening, and tomorrow another good day here in Berlin. Goodbye.